Grounding and bonding are fundamental concepts in electrical safety, crucial for protecting individuals from electrical shock and minimizing fire hazards. Grounding in electrical systems refers to creating an intentional low-impedance path from electrical equipment to the earth. This path allows fault current to flow safely back to the source, tripping a circuit breaker or fuse to de-energize the circuit. Without proper grounding, a fault condition could cause metallic parts of equipment to become energized, posing a significant shock hazard. Equipment grounding conductors, often green or bare, provide this essential path. They connect non-current carrying metal parts of electrical equipment to the grounding system, ensuring that any fault current is safely directed back to the source. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device in the circuit, as specified in the National Electrical Code, often abbreviated as NEC. For example, NEC Table 250.122 provides guidance on selecting the appropriate size of the equipment grounding conductor based on the rating of the circuit breaker or fuse. Bonding, on the other hand, focuses on creating a low-impedance connection between all metallic parts of an electrical system. This includes metal conduits, enclosures, equipment frames, and even metal water pipes. The purpose of bonding is to equalize the electrical potential between these metallic parts, preventing voltage differences that could cause a shock hazard. When a fault occurs, current will flow through all available paths, and if the metallic parts are not properly bonded, a voltage difference can develop between them. This voltage difference can create a shock hazard if a person comes into contact with two differently bonded parts simultaneously. Bonding jumpers are used to connect these metallic parts, ensuring a continuous and low-impedance path for fault current. These jumpers are typically made of copper or aluminum and are sized according to the NEC. For instance, NEC Section 250.92 outlines the requirements for bonding metal enclosures containing service conductors. Grounding electrode systems are a crucial part of the overall grounding and bonding system. These systems consist of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes that are in direct contact with the earth. The grounding electrode system provides a connection to the earth, allowing fault current to dissipate safely. The NEC specifies the requirements for grounding electrode systems in Article 250. For example, NEC Section 250.52 details the types of grounding electrodes that are permitted and the requirements for their installation. The resistance of the grounding electrode system is also an important consideration. A low-resistance grounding electrode system allows fault current to flow easily, ensuring that the overcurrent protection device trips quickly. The NEC generally requires a grounding electrode resistance of 25 ohms or less. If the resistance exceeds 25 ohms, an additional grounding electrode must be installed. Ground fault circuit interrupters, commonly known as GFCIs, are another essential safety device used to protect against electrical shock. GFCIs monitor the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 mA or more between these currents, the GFCI will trip, interrupting the circuit and preventing electrical shock. GFCIs are commonly used in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC requires GFCI protection in specific locations, such as all 125-volt, 15 and 20 amp receptacles in bathrooms. Arc fault circuit interrupters, or RFCIs, are designed to protect against arc faults, which are dangerous electrical conditions that can cause fires. Arc faults occur when electricity jumps between two conductors, creating a high-temperature arc. RFCIs detect these arc faults and interrupt the circuit, preventing a fire from starting. The NEC requires RFCI protection in many areas of the home, including bedrooms, living rooms, and dining rooms. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage sensitive electronic devices. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD divert the excess voltage to ground, protecting the equipment from damage. The NEC requires SPD to be installed in certain locations, such as at the service entrance of a building. Proper grounding and bonding are essential for electrical safety. These practices protect individuals from electrical shock, minimize fire hazards, and ensure the reliable operation of electrical equipment. Understanding the principles of grounding and bonding and following the requirements of the NEC are crucial for anyone working with electrical systems. For example, consider a scenario where a metal enclosure containing electrical equipment becomes energized due to a fault. If the enclosure is properly grounded and bonded, the fault current will flow safely back to the source, tripping a circuit breaker and energizing the circuit. However, if the enclosure is not properly grounded and bonded, the fault current may not flow properly, and the enclosure could remain energized, posing a significant shock hazard. Similarly, if a voltage surge occurs, an SPD will divert the excess voltage to ground, protecting the electrical equipment from damage. Without an SPD, the voltage surge could damage or destroy the equipment. In summary, grounding and bonding are critical for electrical safety. By understanding these principles and following the requirements of the NEC, you can help to protect yourself and others from electrical hazard. Grounding ensures a safe path for fault current. Bonding equalizes the electrical potential between metallic parts. GFCIs protect against electrical shock, FSIs protect against arc faults, and SPD protect against voltage surges. By implementing these safety measures, you can create a safer electrical environment.